Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, continuing our discussion of hot and cold streaks and the gambler's fallacy. Now, we talked a little bit last week about missing some extra points in a row, but just a review of the hot hand in general. We're going to be taking the more positive view that people normally do when they talk about a hot hand, is that if you're playing basketball or something and you make a shot or maybe multiple shots in a row, they're more likely than to make the next shot after that there. Now, one of the things that we talked about last time is this idea of the gambler's fallacy. And I want to remind us of that right away when we're talking about this setup. If things are independent or if things are random, right? If you're trying to apply this to something like coin flips in a row, or if you're doing it to slot machines at a casino, this is not true. There's no kind of idea there of, oh, you're on a hot streak, you're more likely to do this, or if you keep losing for a while, you're due a win. That's not true there, right? One shot should have no effect on the next if those shots are actually independent, right? And the reason this is studied a little bit and kind of thought about that way as well is this idea of the shots being independent is probably not true, right? So we can say pretty clearly here, and I would say most people should be pretty confident that these things are not actually independent. So we're kind of studying, in a sense, well, how close to being independent are there? Can we model these with independence? How could we start thinking about those things as well? So, right, let's review our questions. What if you wanted to test, in a sense, this idea of a hot hand, right? So if you had shots made and missed in some order, what are some ways you might determine something is the hot hand or not? Is this idea correct or incorrect in some scenario there? Now, in question 2, which we will revisit in a second, we introduce this idea of you could look at this with something like, and we're going to use here some data. H maybe is a hit or a make, and then tails will be a miss. So we want to look at some example data and see what we could say with this there. For example, right, we could flip 10 times, right, as some simulation of these kind of misses or makes, and we could start looking at this data there. And what we want to look at, right, is after a hit or after a make. So we might want to collect, well, what's the number of times you make and then make? What's the number of times you make and then miss? So these are things that we might want to look at separately and collect separately here. Right, so if we looked at this make and then make, if we went and looked at our data here, well, we have a make and make heads there. Note if we had a third head in a row, that would be kind of 2 things for our data or something there. We would have another set of heads here as well. So there are 2 outcomes that are make then make. Now, what if we did something similar for the heads tails? What about this make then miss? We could look through our data again, of course, and I'll give some results from some simulations in a moment. These are all things, if you collected the data, you could write a computer program to analyze all of these things and stuff like that there. Now, here's the interesting thing that we could do here. based on our data, right, we could calculate the probability that you make a shot, right, after a make. So this is what we could look at there, right? So we could say, okay, well, we want to now calculate what's this probability that you make a shot after you already made one. So let me give myself a little room here. And in our setup here, based on our data, right, well, we have data for 5 total things, right? There were 5 shots that were made, and then there was another shot taken after them. So this 2 plus 3 would be our denominator, and we would have 2 of those, so this would be 40% there. So small sample size, I'll talk about that in a moment there too, right? But we would say here, okay, they calculate this probability, and based on this 10 outcomes, there would be a 40% chance to make a shot after there is a make there. Now, we would maybe expect that to be 50% right away, right? And that gets us to some of our questions and things like that there. So there was a study, and actually this is one of the first places, at least academically, this idea of the hot hand was introduced. So Gilovich, Tversky, and Vallone studied this phenomenon in a 1985 paper. They did a lot of things, right? But roughly they collected data on makes and misses, both from participants, from looking at NBA games, basketball games, right? They looked for streaks and evidence of a hot hand, right? They actually looked for, and in a lot of real life scenarios, you might say, oh, somebody makes 3 shots in a row, then they have a hot hand. Maybe it's not just after a single shot, which is what we're focused a little bit more on just for ease of use. But they looked for a lot of these different evidences and things like that there. Now, their rough conclusion of everything was that having a hot hand or making a shot or making a series of shots did not affect the outcome of the next shot. What do we mean by affect the outcome? Well, that kind of means if somebody had a 50% chance of making the shot, then after this, if they had a hot hand, it was still 50%. It didn't affect their percentages there. And so the conclusion of this study, or rough conclusion based on this data, was that this hot hand did not exist. The data they found did not have evidence of the hot hand there. Now, things, of course, actually turn out to be a little bit more complicated there. So, of course, it's better to look at real world data, but let's just do the pure simulation route here. I talked about heads and tails before, heads being a make, tails being a miss, right? We would expect 50% of shots to be made. And question 2 from last time was, do this with random outcomes and look for the evidence of a hot hand, right? Gambler's fallacy would tell you that this kind of should not exist. There's no hot hand for a coin flip or things like that there, right? We want to analyze that data and kind of see what it says and look at it there. Notice this is roughly what they were doing in the 1985 study, right? You're looking for streaks, right? You're looking for kind of things like that there as well. Now, we'll get to some experimental results that I collected from this with these simulations in a second. But this is exactly what a paper from 2018 did, reanalyzing the data from 1985. Now, I want to break down their rough, again, conclusions from that 1985 study. They first said that having a hot hand did not affect the outcome of the next shot. And then, right, their conclusion based on that was that thus the hot hand does not exist. Now, a new analysis in 2018 had some interesting results. So this paper in 2018 by Miller and Sanjuro suggested that because of these sampling biases and small sample sizes, the paper should actually have the opposite conclusion. So this new paper did not do anything in terms of the data collection or things like that there. They weren't doing the study that way, collecting data or recollecting data. They were analyzing the same data. So the same analysis was happening with the same data there. They totally agreed with this first conclusion, right? Okay, if somebody has a hot hand, the next shot they make is at their normal percentage. It does not affect the outcome there. And what they actually argued, which is the interesting thing here, and what we'll talk about quick in the conclusion of this video, is that this second thing here is not true. We need to be careful with this conclusion there. And this is a little bit weird and a little bit hard to kind of understand in that case, right? And so let's look at some experimental data and the kind of sampling bias that's happening. So, right, the example here is, let's say you look at the data with those coin flips, n coin flips, and calculate the probability of an H right after an H. In a given experiment, should you expect to get 50% here? And this is what the analysis that Miller and Sanjuro kind of were talking about. The actual answer here is no, right? We have this idea of small sample sizes, right? And so we have the problems, let me say, we have kind of a small sample and so this is introducing what's sometimes called in statistics a sampling bias there. You can actually run these simulations. You can actually calculate this directly for small numbers there. I only did it for n equals 5. The other numbers are all simulated probabilities, so maybe they're off a little bit there. But, right, to explain these numbers, I'm saying you flip a coin n times and you do this, is there a hot hand analysis there. For those experiments, so if you do this, right, and do it again and average all of your results. So you find the result, find the probability, find a second result, find the probability, average the results, you actually get less than 50%, right? So you actually should get less than 50%, meaning if the probability in the data says that the next shot has a 50% chance of going in, that's actually evidence of the hot hand here, right? So I'm not going to talk too much about the bias, but the idea is for a small number of coin flips, right? So example, first off, think about 5 flips there. First of all, is any shot happening after the 5th flip? Is any flip happening after that 5th one? No. So already that 5th one is kind of different because it affects the 4th one if you're looking for a streak. But right, other than that, it doesn't exist for a next shot. There's no shot after that there, right? And little streaks like HHH, that's all of a sudden giving us, okay, a shot and a make, another make after that, a make after that. So you have these runs because of the small sample size and the different variants of stuff there, right? You actually kind of are messing up some of these probabilities, right? If you did this for huge numbers, if you looked at a sequence of 2,000 shots. Of course, it's going to be 50-50 if we just flip the coin. But for small sample sizes, right? If you're looking at a game, maybe the player only shoots 20 shots that game, right? You're getting these small sample sizes and the bias that's coming in there. To end, does this contradict the gambler's fallacy? No, right? We want to be careful not mixing results on a full sample of flips, right? We flip the coins, we're looking back at the results and results on individual flips. Sometimes this would be descriptive statistics when you're studying a whole sample or population versus predictive statistics. And you want to be careful not mixing those things there. And as our kind of last word on the hot hand, does it exist? Probably, but it's probably dependent on the player. Maybe some players have a hot hand, some do not. Might be evident or dependent on other circumstances, whether the player is playing in their home gym or in an opposing team's gym, right? Real life stuff is complicated. And that's one thing that's kind of interesting about applying statistics and applying the mathematics of things to the real world. You want to be careful with the assumptions you're making, and when you're trying to model something from the real world, being cognizant of those assumptions and how that might affect your outcomes and introduce biases into things as well. Thank you for watching. Give this video a like and subscribe to our channel if you want to stay tuned for other updates coming later on as well. Otherwise, thank you all for watching, and I will see you all next time. Goodbye.